All right, one of the things we're going to be doing is we're going to be graphing the behavior of acids and bases as an acid is neutralized in order to analyze what kind of acid we have. Okay? And so you'll be producing a graph. And your graph will have pH on this axis. Okay? And on this axis down here, you're going to have the amount of base solution. And maybe I should say it's volume of base solution added. Okay? Now, of course, when you do your graph, you need to specifically identify which base we're working with and so forth. Okay? But what we're going to examine then is we're going to use this behavior on the graph to figure out what class of acid we have. What classification of acid we have. And we can figure out several things. We can figure out whether the acid is and we can figure out a lot more than what we're going to do on Monday. We can figure out the things that we should be able to figure out is whether is the acid strong or weak. Okay? We can figure out is the acid monoprotic, diprotic, or triprotic. We can figure out what the equivalence point is. We can determine what amount of base solution was added at that point. And we can determine what the acid concentration is using stoichiometry. And you're going to be doing all these things using Monday's lab results. Yep, equivalence point. I want to define for you what an equivalence point is. This occurs when the concentration of protons, also called hydrogen ions, or simply H+, is in a perfect 1-to-1 ratio with hydroxide ions. An equivalence point occurs when the concentration of protons, which we also sometimes call hydrogen ions, or symbolize it simply as H+, is in a perfect 1-to-1 ratio with hydroxide ions. That's what an equivalence point is. Now, that's not what it looks like on the graph. We're going to show you in a minute what it looks like on the graph, or on a graph. Okay, let's see. I think that water's finished running long enough. Would somebody just go ahead and turn that off from table number 1? I had somebody making up a lab this morning, and I want to make sure we have rinsed everything down the sink completely. So we left the water running. Sorry. Chemistry lab, you know? All right. I'm going to go back to the graph now. So, on the in your lab on Monday, you're going to be given an acid that you don't know what the acid is. You're going to be what you're going to do is figure out several things about that acid. Okay, and I mentioned those here. Okay, you're going to tell me, is it a weak acid or a strong acid from this graph? You're going to tell me, is it monoprotic, diprotic, or triprotic? You're going to tell me, what is the equivalence point? What amount of base solution was added at that equivalence point? And then you're going to stoichiometrically calculate the strength of the acid using this data. Okay? So let's start with what a strong acid would look like. Now, this is a generalization. Not every strong acid looks exactly the same. So you have to use some good judgment. Okay? This is where creativity comes into play. A strong acid, let's start with a strong monoprotic acid. Strong monoprotic acid. Write it down. Strong monoprotic acid. A strong monoprotic acid is going to start down near 0 or even below. Now, it might not start at 0 if it's already been diluted or something, but it's going to be down there somewhere close to it. But the pattern is going to look something like this. Yes. No. It means that the pH of the acid, when I started, before I start putting any base in there, the pH of the acid is down near 0, maybe even below 0. Okay? And as I add base to it, the pH starts slowly to go up. Okay? The pH is going up until it starts to make this really steep climb. And then it'll start to narrow out again as I add more and more base to the solution.
That's not what product means?
No, that's not what product means. I'm going to tell you what product means in a minute. Okay? So a strong monoprotic acid will generally have this pattern. Now it might look a little bit different. This, what I like to call the cliff face, the straight up and down part, or nearly straight up and down part, might be a little over here, a little bit over here, but basically you got one big cliff face. Does that make sense? That's what a strong monoprotic acid will look like. If we start down near zero or below, and you get a really strong cliff face, one of them, and it makes this sort of lazy S sort of curve. All right? What? Do I have an eraser? You got $1? You have to leave a deposit of $1 to use my erasers. Now, we know it's a strong acid because the curve starts down here near zero or below, or looks like it might have started there. If it's already been diluted and I was starting somewhere along here, it looks like it might get down there. Okay? All right. So that's how we know it's a strong acid. We know it's a monoprotic acid because it's only got one cliff face. We know it's a monoprotic acid because it only has one cliff face. Okay? The equivalence point on this graph. Now remember what an equivalence point is, by definition, is when the number of protons equals the number of hydroxides in solution. Okay? The equivalence point is in the steepest part of the cliff face. The equivalence point is at the steepest part of the cliff face.
So what is the what?
What is the what? The equivalence point is the steepest part of the cliff face. Got that? So, by looking at the shape of the graph, we can tell it's a strong acid. By looking at the shape of the graph, we can tell it's monoprotic. From the equivalence point, we can figure out the rest of the things we want to know. What amount of base was added at the equivalence point? Well, to find out how much base was added, all we got to do is have a vertical line that goes right down here and read how much base was added. The equivalence point is identified by the pH. Okay? Okay, so we're going to determine what the equivalence point is by the pH. So if this equivalence point is a pH of 7, that's what we say. The equivalence point occurs at a pH of 7. Does that make sense? Okay.
So we can follow that line all the way to the left.
To identify what the equivalence point is, you identify it by the pH. So you can say the equivalence point occurs at pH of 7.2 or something, whatever it happens to be. Got that? It's the steepest part of the cliff face. It might or might not be the middle. Okay? Steepest part of the cliff face. All right. You're not finished? All right, let's hurry up. Gotta move along. Don't have a lot of time. Time's a waste and daylight's burning. All right. Like I said, not all of these graphs are going to look the same. Sometimes they look like this, or something like this. Very good. For those of you on the video who didn't hear it, one of the students identified this as diprotic even before I said so. And that's what I said very good about. Okay? Now, we should already be able to determine whether this is a strong or weak acid by what I told you about the last graph. Is it strong or weak? This is a strong acid, and we know that because it appears to start at or below 0, or if it wasn't concentrated enough to start with, it appears that it would have started there. If you had extended the curve or the graph backwards, it appears it might have started at 0. Okay? Now, this graph has 2 equivalence points. We have an equivalence point here and an equivalence point here. So just the shape of the graph tells us that this is a strong diprotic.
Is that a circle? I mean, an A with a circle?
Yep.
Or is that an X?
A with a circle around it.
Okay. Why you guys get smart?
We can identify the pH of both equivalence points by going from where it crosses the curve to the left. That would tell us the pH of both equivalence points. We can tell how much base was added when we reach both those equivalence points by going vertically down. Does that make sense to everyone? Okay. So now we're going to define what diprotic means. Okay. Diprotic acids have 2 hydrogen ions that can dissociate. An example of a diprotic acid is sulfuric acid. When the sulfuric acid is very strong, that is, it's very concentrated, let's put it that way. When it's very concentrated, you have a very low pH. Remember, acids have a low pH. Okay? And most of the acid is in this form. Okay? As we add base to the solution, let's say we're going to use KOH as our base. This is potassium hydroxide. You've seen that before. As we add more base solution, the first hydrogen comes off of this. And so as we move up here, we start to take more and more of that of the formula units here, all the millions and millions and millions of these formula units that are in our solution. As we add more KOH, we're pulling off one hydrogen. And the result is that we have one hydrogen removed, and we're making this stuff right here. The hydrogen that gets removed is joining up with the OH, so we're also making water. And we're freeing some protons. Or not some protons, some potassium ions. Okay? When the number of hydrogen ions pulled off the acid is equal to the number of hydroxide ions, we've reached that equivalence point. And we can know that the number of hydrogen ions removed and the number of hydroxide ions in solution are equal because we've got the steepest part of the cliff face. Okay? And since that means that we have an equal number of these things, okay, hydroxides and hydrogen ions are equal, at that point we can use the amount of base to calculate the amount of acid we started with, stoichiometrically, because it's a 1-to-1 ratio, just like the equation shows a 1-to-1 ratio. Okay? The balanced equation has a 1-to-1 ratio between this and this if we're only pulling off the first hydrogen ion. Okay? So where do we get this other cliff face up here? Okay? I'm going to tell you. We're going to be pulling the hydrogen off this species right here. I'm sorry, we're going to make this C. So this is where B occurs right here. Like at that first cliff face. All right? Then we're going to take this species here, and we're going to keep adding this KOH. So now another hydrogen is going to be removed from this. And when I pull a hydrogen off of this, I have just the SO4. But now I'm pulling another positively charged particle off. What's the charge on this thing? If this is a 1 negative charge, and I pull a hydrogen ion or proton off, what charge does this species have? Huh? No. 2 negative. But I already have 1 negative. I'm pulling another positive charged particle off. You make it 2 negative. Okay? And you will find this polyatomic ion on your common ions list. And we're still making water. The hydrogen from this species here, this is called bisulfate. This hydrogen joins up with this hydroxide on the back. We're making more water. And we're still freeing up more potassium ions. Alright? So this is called bisulfate, if you want to know. I think it's on your common ions list too. And this is the sulfate ion. Okay? And this is just our base again. Alright? So this, when this number of hydrogen ions and hydroxide ions is equal, when this number from this species of hydrogen ions and hydroxide ions is equal, then we get to this point on the graph, where this equivalence point is located. Hmm? So as you do this lab on Monday, every lab group will have a different acid. You will not have the same acid as the next person on the next lab group. Or you'll have the same one as everybody at your lab table does. But every lab group is going to have a different acid. You're going to have a different graph. You're going to have to interpret each of those graphs and determine your concentration based on your results. Okay? Any questions about that so far?